This is a short talk about understanding consciousness, and it makes a number of claims, some of which might seem a bit outrageous to people. The main claim it makes is that we can make important progress in understanding consciousness, and we can make it now. Now, that claim may seem outrageous because people have been studying consciousness for quite a long time now, and very little progress has been made recently. So the idea that we can make some progress may seem an outrageous one. The second idea is it's a scientific problem, not a philosophical problem. That's not so controversial. The third idea, which is controversial, is that the answer, the thing in the brain that causes consciousness, is simpler than we think. Now, I shall start by talking about what I think are two blind alleys in consciousness research. One of them is qualia and the other is neurons. I don't think either of those are parts of the problem we ought to be studying. In contrast, I think consciousness is about geometry and space, and we can understand important aspects about it in that way, and that it happens in the thalamus. So blind alley number one is qualia. We all know the ancient philosophical problems of qualia, that I have a sensation of red and you have a sensation of red, and your red might be completely different from my red, it might be the same as my blue, and we can never test this, we can never have a discussion between us that resolves that question. The question is, so what? If there is no experimental test of the nature of qualia, then that's a bad place to do science, because science is the art of the soluble and the testable. So we can test important things about consciousness without solving the qualia problem. So let's put qualia on one side and move on. Blind alley number two, which will be more controversial, is neurons. Now, everybody knows, or people think, that one neuron firing is not conscious, nor is one transistor firing. Now, the consequence of that, you might think, is that many neurons firing is not conscious, but a lot of people resist that conclusion because that's what the brain is full of, so they think lots of neurons must be conscious. And they justify this by talking about emergent properties. They say consciousness is an emergent property from lots of neurons firing together. Now, that makes it look scientifically respectable, but it's not really, because emergent properties only emerge when there's the right piece of mathematics that shows they should emerge. And for consciousness, there's no such piece of mathematics. The only piece of maths that I can think of that applies is that the sum of zeros is zero. In other words, you've got zero consciousness in one neuron, then in a whole pile of neurons, you have zero consciousness as well. Now, another completely separate point is that neuronal theories of consciousness, of which there are a few, say nothing about the properties of consciousness. They say, well, there's this or that configuration of neurons doing this or that computation, and wow, there's consciousness, it exists. They don't say anything about the properties of it. And because they don't do that, they are untestable. So the viewpoint I'd like to take is that neurons are not conscious, and again, we should move on and look somewhere else. So where should we look for consciousness? Having fewer places to look is actually a good thing because it constrains the search. But let's step back and think what animal brains do. They are there to control muscles, really, and to help the animal to make appropriate movements, because that's what animals can do that plants can't do. So in order to make appropriate movements, brains have to understand local space. They have to understand local objects around the animal in space at the present moment. Now, brains compute, and computing is a mathematical operation often, and if the right maths is built into the computer intrinsically as part of its mechanism, it's much more efficient and accurate and fast. So what's the right maths? To understand local space, the right maths is three-dimensional geometry. Now, we know that neurons do three-dimensional geometry rather badly. Very few people have tried to model this in neurons, but if you do, you find it's very inefficient. You try and represent a point in space by 3 dimensions, 3 neuronal firing rates, and it's very slow and noisy and so on and so forth. So how can we do three-dimensional geometry in the brain? To understand how, think of maps. Now, if you're walking around some area, to understand where you are, you look at a map, and a map is an analog representation of two-dimensional space. Now, maps do two-dimensional geometry intrinsically, and they do it very well. For instance, if 3 points are collinear on your map, it's a pretty good bet they're collinear in real space. Or if the distance between 2 points is big in the map, it's going to be a big distance in real space, and so on. So a piece of paper, a map, does two-dimensional geometry, and it does it really well. There's a lot of geometry that comes free in a map. So how can we extend that to 3 dimensions? How can a 3-dimensional map of local space exist in the brain? As I say, I don't favour neurons for that. Neurons do 2-dimensional maps, point by point, rather well, and there have found lots of them in the cortex, and they work. But a 3-dimensional map, point by point, if you have a clump of neurons in 3 dimensions with the position of the neuron representing the position of the point in space, that works rather badly because you can't get the data in and out of this clump of neurons. And beside that, nobody's ever found a 3-dimensional neural map in the brain, I don't think. Let's take a different tack and look at possible wave excitations in the brain. And the hypothesis is that there's a wave excitation in the brain which is a Fourier transform of local space. In other words, the wave excitation has a lot of different wave vectors in it, and each wave vector represents a different position. And by superposition of the waves, the whole wave can represent lots of objects at different places. And neurons somehow couple to the wave, they can input to it and read from it. Now, if you have that sort of thing happening in the brain, Fourier transforms do geometry rather well, because the simple maths of it, which says geometry in real space translates to geometry in the waves, and all sorts of geometric relations translate easily between one to the other. And in a Fourier transform representation of position, there's no distortion, and we know this from holograms, which are Fourier transforms of spatial information, and they have no distortion, and they're rather robust as well. A small proportion of the hologram can represent all the same information, just at lower resolution. So the proposal is that's how the brain does geometry. If we think there's a wave excitation, where is this wave excitation in the brain? Well, the proposal is it's in the thalamus. The thalamus has all the right connections to hold a model of 3-dimensional local space, because all sense data comes through it except smell. And that's quite significant, because smell data gives you no good information about the position of things in local space, because it wafts around and you don't know where it comes from. And so the fact that the thalamus has all kinds of sense data except smell, I think, is rather significant. And the thalamus connects to all parts of cortex which process the sense data. So that's the positive argument that it might be in the thalamus. There's a strong argument that there's a wave excitation in the thalamus, because without a wave excitation, the anatomy of the thalamus doesn't make sense. And this problem is, why are all the different thalamic nuclei bunched close together in one lump in the middle of the brain? Because they don't connect to each other. This is the main finding about the anatomy of the thalamus, that different thalamic nuclei don't have strong neural connections. And so if you were trying to save energy in the brain, over evolutionary time the thalamus would have exploded, with each nucleus in the thalamus migrating outwards towards the bit of cortex that it talks to. And if that had happened, the axonal distances that you need to make the thalamus work would be much reduced, and so you would save a lot of brain energy consumption by the shorter axon. So the anatomy of the thalamus all bunched together in one place does not make sense on a purely neural connectivity model of the brain. But a wave excitation in the thalamus storing 3D locations makes sense of all this, because the different thalamic nuclei would all have to be in the same region in order to be inside the wave. So if there's a wave excitation in the thalamus, why haven't we discovered it? Well, I think simply we haven't looked at the thalamus with the right probes and the right resolution to discover it. And so the hypothesis is that there is a 3D wave in the thalamus, that represents local space and the objects in local space, and consciousness arises from this wave. Now, there's a piece of very important confirmation of that idea, because consciousness, if you think about what you're experiencing now, you have these qualia, but Mainly, consciousness is an accurate three-dimensional model of the space around you at this very moment. And the qualia you experience, that green colour in the leaves, is located in that three-dimensional local space. And it's a very accurate three-dimensional model of your local space as well. And this is a huge experimental fact about consciousness. In fact, I think it's the main fact. And the strange thing is that current neural theories of consciousness totally ignore it. And the reason I think they ignore it is because they have no clue how to explain it. But this theory explains it naturally. It says there's this wave in the brain, in the thalamus. This wave represents the positions of objects, and that is the cause of consciousness. And this gives an evolutionary reason for consciousness, because brains are there to control movement. To do this, they need to represent local space and do it very accurately. And consciousness arises from the wave that's involved in doing this. But there's an objection to this theory. Why should a wave be conscious any more than a neuron is conscious? We know lots of different waves in the world. And the proposal here is that the wave in the thalamus is a Bose-Einstein condensate, like a superconductor, like a superfluid, and so on. And this idea would have a lot of advantages for storage of spatial information, because a Bose-Einstein condensate, which I'm calling a BEC, stores information for long times, like superconductors that can store a magnetic field for an infinite time. It's very proof against thermal noise, it uses very little energy, and so it'd be very suitable for storage of information in the brain. And so the proposal is that evolution has somewhere discovered a Bose-Einstein condensate in the brain, and my question is, why shouldn't it have happened? Evolution has discovered lots of other very clever things. Now, a Bose-Einstein condensate is a very rare and distinctive state of nature, and what it means is that there are billions or more than that of quanta, all of which are in the same quantum state, and that's a rare state of nature. And so the proposal is that consciousness is, or arises from, billions of quanta, all in the same quantum state. And that, if you like, is a proposed new law of nature. And what it would mean is that every Bose-Einstein condensate, like a superconductor, is somehow conscious of its own state. But the thalamus holds the only Bose-Einstein condensate in nature, which is connected to sense data, which is representing local space now, and is connected to a computing machine, which is the neurons in cortex. So that is the hypothesis, and as I say, it's a big claim because it's actually explaining what consciousness is, how it arises, and why it feels like it does, why it feels like geometry. Many of these ideas are not new. I think this theory is just tying them together in a package which accounts for the main fact of consciousness, which is this beautiful, accurate geometry that we have in the consciousness we experience. Obviously, this proposal impacts not just consciousness, but the whole of neuroscience, because it's saying the key thing that's happening in the brain in the middle is a wave excitation, and so neurons are not the only story. So this is a big hypothesis. If you can prove it wrong, if you think you know why it's definitely wrong, please write and tell me why. But otherwise, please think about what it means and how it might be tested. So don't just get back to the day job. Think about this idea and try and think how one might test it. If you want to find out a bit more about it, there are some papers on my ResearchGate site, which is the website just below.